All right, good morning. So here we are in lecture number 6. Today we're going to talk about the linear model. This is the first of a series of lectures on modeling. Well, actually second, I could say, because the first one we talk about modeling in general. Today we're going to talk about a specific family of models, which is the linear model. And so within, again, the scope of the course, we are going to be talking today about this part here, about modeling and learning something useful from a model. And we're going to start doing that with linear models. And so in this lecture, we're going to talk about linear models in general. We're going to start with a simple linear model, and then we're going to bump it up a little bit towards the multiple linear model. And then we talk about more or less same things we talked about in the last lecture. So given multiple choices for a model, how do we select? How do we choose one model? How do we fit the model? And then we'll talk about something specific of the linear model, which is dummy variables to encode categorical predictors. We're going to talk about interaction effects. If you remember something from the first lectures, we're going to see how to model those interactions between factors in a linear model. And then finally, just a little bit about transformations and some common misunderstandings when it comes to transforming variables. So let's start. The linear model. So the linear model is one in which we assume the relationship between the covariates. Remember, the covariates are the independent variables, features, predictors, whatever you want to call them, the x's. So what we assume is that the prediction is, the relationship is linear. And the thing is that this is a simple model. Very simple in its nature. It can get very complicated, as you will see today and on Wednesday. It's maybe even unrealistic because we know that the relationship between variables normally is not linear. It has some non-linearities. But anyway, it's going to be very useful, both conceptually, because it's going to allow us to ask very useful questions. And actually, it's kind of the basis for most of the statistical work that we can do nowadays. And they're very practical because they're simple. That's why they're beautiful, because they're simple. And so here we have an example of a data set. This data set is about advertising. And here we have data about some product. I don't remember which one now. But what they had was how much they advertised the product in terms of advertisement on TV, on radio, and on newspaper. So this is a numerical variable. And I believe this was in $1,000. So 200K around here. And then in the y-axis, we have the sales. So this would be the response, the outcome. And what they are interested in looking at here is what's the relationship between how much I spend in each of these three media outlets and how much the sales increase or not decrease, or see what the relationship is. And yeah, we can just draw a line, so to speak. That would be a linear model. And we will see that in some cases, this is a good thing, in some cases it's not. So for example, here in terms of newspapers, we see that the relationship is more random-like, but still we could try and draw a line to see what the pattern is. Is it increasing or is it decreasing? And then we might have something like what we invest in the TV advertising, and we see that it's kind of increasing with very large values. We're going to talk about this later, and we see that it's even non-linear. So probably if we draw a line somewhere around here, that would be a better model. But anyway, for simple things like do the sales increase or decrease with the TV advertising, a simple linear model is fine. So what kind of questions can we ask with a linear model? Well, we can ask, for example, is there a relationship between the outcome and the predictors, between the y and the x's? How strong is the relationship? What predictors are more important in modeling or in understanding, in predicting the outcome? Which are the x's that seem to be the most important? And how well can we predict new observations? So if we model linearly all the predictors, how well can we predict the outcome? Are there relevant interaction effects? So is the effect of one x dependent on the value of some other x2, or is it independent? So these are the kind of questions that we're going to be able to ask with the simple linear models. So let's get into it. Simple linear model. The simple linear model is one in which we take this form here. We say the outcome, the variable y, is just a function of the x, only one predictor, only one feature, and that x is going to be attached to one coefficient beta 1. Then we have another coefficient beta 0, and of course some error in the model because the model is not perfect. So the model would look something like this. It's essentially the relationship between two variables, two numerical variables. And how do we interpret the coefficients? The coefficients of the model would be beta 0 and beta 1. Beta 0 is what we call the intercept, and it's essentially the value along the y-axis that the line crosses when x equals 0. So it's essentially this magnitude here. What is the value of y when x equals 0? And then we have beta 1, which is attached to x, and we call that the slope. We call it the slope because it's essentially modeling how much does the y increase for the unit increase in x. So it's kind of measuring this angle here. Is it a steep line or is it not? And so these betas are known as the parameters or the coefficients of the model. So whenever we want to fit a model, talking about the previous lecture, we would say the family of models would be something like this, and then one specific instance of the model would be one in which we fit or set specific values for beta 0 and beta 1, and that determines a model something like this. So how do we estimate the parameters? The idea is, again, given some training data, we can find estimates, beta 0 hat and beta 1 hat. Remember that the hat means this is an estimate. So that essentially means we fit a specific model, f hat, such that given some x, we can basically make a prediction about the y. So we can have a y hat given some input value x. And so the goal is again to find good estimates, to find a good model. So what are the values of beta 0 and beta 1 that are optimal in some way? This is what we refer to by fitting the model. So how do we do it? Well, to illustrate, assume that we just fitted the model. Imagine that we already have it. We already know the values, the best values, beta 0 and beta 1. So the model would be something like this. And we could make the prediction for every known observation in the training data. So for every ith observation, we can actually make the estimation. What is the y sub I? Then we have the concept of the residual. And the residual is a value that every observation has. And it's essentially what is the difference between the true value in the data set and the estimated value from the model. It's just a difference. So if you see the picture here again in the scatter plot, it's essentially the length of these lines over here. So what is the distance between the true observation and the value of the model for that one specific value of x? And so you see, if the residual is positive, that means the model is underestimating the value for observation y, because this means this value is larger than that one, so the model is underestimating. So it would be, I don't know, an observation something like this one. This one is being underestimated because the model is predicting something lower than the true value, and vice versa if the model is overestimating. So this is what we call the residual. And again, it's something for each observation. What is the difference between the true value and the estimated value? And so if you think about it, we can define this residual sum of squares, which is just the sum of all the residuals in the training set squared. Why do we square it? First of all, so that the sign of individual residuals doesn't have any effect. So we count all distances the same. They are all going to be positive. And it's also going to magnify large residuals. So if we have a model in which one specific observation has a very large residual, that large residual should be penalized more than others. And as we will see in the next lecture, it just happens to have interesting theoretical properties. We will talk about it in the next lecture. So you could think about the model or fitting a model as the process of finding the coefficients that minimize the residual sum of squares. So what is the line that minimizes the distance between the true values and the observations? The predictions. And so it turns out that if you do the math, we have what we call ordinary least squares regression, and it comes exactly from minimizing these sums of squares. And it turns out that the coefficients, the estimated coefficients are here, beta 0 and beta 1. So you see everything is about the distance between the observations and their mean values. So you have it over here. And doing that, we can obtain the optimal coefficients in terms of minimizing the sums of squares. So here we have a very simple way, an intuitive way of fitting a linear model. It's just choose the coefficients that minimize the sums of squares in the residuals. So let's see what happens. Imagine that we have the following true model. Again, we never know this, but for illustration purposes, let's assume in reality, the relationship between X and Y looks something like this. So this is reality. And then we're given some training data. We observe some training data or some observations, sorry, from our study. And each of those observations are these points in here. So if we fit the model, in this case, we find this red line. That would be the model estimated given the training data. And of course, it's not going to be exactly the same model. We know this from the previous lecture. There's going to be some degree of error. If we gather some different training data, then we might have a different estimated model. And in this case, you see the model is a little bit different. This is fine. So the question is again, the fitted coefficients are going to depend on the training data. Which specific model you end up with is going to depend on your data. So here's where the model variance comes from. So looking at the example that we saw earlier about the relationship between the sales and the TV advertising, if we assume the following class of models, again, just a linear model of one variable, the TV, then it's about fitting coefficients beta 0, beta 1. If we do the ordinary least squares regression that we saw earlier, it turns out that the estimated model as a function of the TV is the following. So this would be the estimated value for beta 0, and this is the estimated value for beta 1. And so what the model is saying is the relationship, if we assume a linear relationship, looks something like this. So you see, this is again beta 0. This is the point at which the line crosses x equal 0. And then we have a slope of 0.048. So that means for a unit increase in TV, the sales go up by 0.048. Now, whenever we fit the model, it's a very good idea to take a look at the residuals. So what is the distribution of residuals? And essentially, we're looking for two things. The first one is if we plot the histogram of the residuals, it should be kind of symmetric. So it will always be centered at 0 by definition, but it should be kind of symmetric. And in this case, we see that it's not. There seem to be more observations with a positive residual than with a negative residual. It appears to be. That's something that we have to check. That is, or that means that the model could be probably improved to make better predictions. And the other thing that we like to look at is the scatter plot of the fitted value. So this would be the y hat and the residual. So what is the residual for that one specific observation? And we look at this because it should look like a completely random cloud of points. If we see patterns in this scatter plot, that means we are missing something. We are missing either a transformation of the variables, we are missing other variables, we're missing something in the model because there is a pattern in the residuals. And if there is a pattern, that means there has to be something else to explain the variable. If it looks like random, then that's good. So in this case, what we see is that, first of all, there's something out here for low values of TV advertising. All the residuals are negative, and we see clearly this pattern in which for large fitted values, we have larger residuals. So we'll talk about this kind of thing later on. But anyway, again, whenever you fit the linear model, it's a good idea to look at the residuals, see how they look. So visually, we can kind of diagnose the model a little bit by looking at the residuals. If we want to start quantifying the accuracy of the model, how good the model is, then we have different metrics. One of them looks at the standard error of the residual. So if you look at the thing here, you have the residual sums of squares, and it's essentially making it kind of independent of the number of observations. Again, there is a word for this. I forgot also in the last lecture. Make it invariant to the number of observations. So again, if this is large, that means the model is having very large residuals. So that's probably a problem. Something that is more intuitive in a way is what people call the root mean square error. So it's essentially you get the error, you get the square, you get the mean, and then you get the root square. So it's essentially something like what is the expected residual, and this is typically what people use when they use linear models for prediction. Typically, what they want to do is minimize this quantity, the RMSE, because it's essentially just looking at every observation and how large the residual is for every observation. And so typically, if all you care about is the prediction, the quality of the prediction, normally you refer to the RMSE. If you look for understanding, you look to at the model for the purposes of understanding the data. Normally we use what we call the R-square, or the coefficient of determination. And the formula, it's a little bit intricate if you want. So we have the total sums of squares. So you get every observation here and you get the square deviation from the mean. So this is a measurement of how much variation there is in the data, in the response, regardless of the model. And then here we say subtract the residual sums of squares. And if you see it, it's a fraction over the total sums of squares. So what we're saying here is this is the amount of variance that we don't know about in the model, so what we cannot explain, the residuals, and this is the total variation in the data. So what we're saying is how much of the total variation in the data does the model explain? This is exactly what this R-square is doing. So again, it's the fraction of the observed variability in the response that is explained or accounted for somehow by the model. So everything that the model cannot explain is here in these residual sums of squares, and it's just a fraction. And it turns out that in this case of the simple linear model, if you get the Pearson correlation between the two variables and you make it square, you got this quantity precisely. And that's why it's called R-square, because for the case of only one variable, the two things are exactly the same thing, the square of the Pearson correlation and the R-square. And so this thing ranges between 0, the case in which there is no predictor, in which the model would be something like this alone. There's nothing. We're just trying to see what is the average. And one in which the R-square equals 1. So that would be the perfect model, one in which all the residuals are 0. So whenever you have an R-square that is high, that's good. If your R-square is low, that means you're still unable to explain most of the variance that you observe in the data. So the model is lacking something. And as a question for you to think about, here we have, does the R-square equal 1? So that means if I have an essentially perfect model that goes through all the observations, no residuals, does that imply that the estimate that I have for the coefficients are the true coefficients? Think about it. We can talk about this question next week during the Q&A. All right, so this is how we can measure the accuracy of the model. So again, for our example, what do we have? If we run the numbers, it turns out that the RMSE is 3.2. So that means the average residual is about 3.2 units in the sales. And the R-square is 61%. That means this model is able to explain 61% of the variance in the sales, or the variability in the response. And again, is there still anything odd about the model? We saw earlier that yes, because all the predictions here tend to be overestimating, and there is this pattern in the data. We're going to see about this later. So this is the linear model. Simple linear model in which we only have, again, one predictor. What happens if we want to include more predictor, more excess? And in particular, let's say that we include P predictors from X1 to XP. Then the model has the following form. It's something like the response equals some common intercept. We still have this beta 0. And then every coefficient is going to be attached to one variable. So we have beta 1 for X1, beta 2 for X2, all the way up to beta B for XP. So it's just a linear combination of all the factors. And again, beta 0 is what we call the overall intercept. And beta j, each of these, beta 1, beta 2, beta 3, etc., is still a slope. Is still a slope of the hyperplane. We're going to see a picture now. Well, actually, let me show it now. Imagine here we have the linear model in which we try to model the y as a function of x1 and x2. And so in this case, the model is not a line, it's a plane. And exactly what the coefficients are is here along the y-axis we have beta 0. So what is the point in the y-axis when both x1 and x2 equal 0? So that would be this height. And then we have beta 1, which is along the x1 axis. It's measuring this slope. And then we have x2, which means along the x2 axis, what is this slope over there? So this is what the coefficients are. And this is beta 1, and this would be beta 2. And so they are still a slope. It's just a slope in each of the individual dimensions of the space. And what they mean is what is the average effect of the response of a unit increase in xj, holding all the other predictors fixed. And if you remember from the other lectures, we are again referring to this, everything else being equal. So this beta 1 tells me how much the y increases or decreases for a unit increase in x1, holding everything else in the model the same. So because of that, the model is now going to be more difficult to interpret than in simple linear regression, because we have this effect of the other variables that we cannot just remove when we look at this individual coefficient. We cannot look at individual coefficients without considering the others. We're going to see examples. So anyway, this is the multiple linear model. It's just adding more terms to the equation. And so let's use the same data set. And now let's say that we want to build a model of the sales, not only as a function of the TV, but also as a function of the radio and the newspapers. So how much we spend on the 3 media outlets. If we do the ordinary least squares regression again, so that is find the coefficients that minimize the residual sums of squares, it turns out that the model looks something like this. So it's the intercept now 2.9. So I'm going to write here, this would be beta 0, beta 1, beta 2, beta 3. So a certain amount, this will be interpreted somewhere like, if I don't invest anything on advertising, how much do I sell of my product? That's what the interpretation of the intercept gives us. And then we have how much does it increase for a unit increase in TV, in radio, and in newspaper. And you see there's something weird here. It says that if we spend money advertising on the newspaper, our sales are actually going to go down by a tiny little fraction, only 0.001, but it's going down. And the question is, does this make any sense? Probably not, if you know about this domain. So what is the problem here? Does advertising on newspaper have a negative effect on the sales? Of course not. And actually, if you look at the data, if you just plot directly the newspaper here versus the sales, you're going to see that, yeah, the relationship is a little bit fuzzy, it's a little bit noisy, but if you draw the regression line, if you fit the model only sales equals beta 0 plus beta 1 times newspapers, if you build that model, it's got a positive slope. So that means advertising on the newspapers is going to give you more sales. So why is this coefficient negative here? And hey, if you look at the simple model that we had earlier, only TV, these were the coefficients. And we look at the multiple regression model now with the other coefficients, we see that the models are completely different. So for example, the intercept is very different from 7 to 3. The effect of the TV is more or less the same, 0.48, 46, and now we have this effect of radio newspaper. And again, why is this negative if we saw that the relationship is actually positive? Well, what this is saying is not that advertising on newspapers has a negative effect. What it means is that in the model, if I already have the value of the TV and already have the value of the radio, adding the newspaper is probably not going to give me any more information. And actually, you can look at it as a way of correcting the model in which we only include these three coefficients. It's doing something like that. So it's kind of like if we only incorporate the TV and the radio in the model, it's going to overestimate a little bit. And it turns out that that overestimation is correlated somehow with the advertising on the newspaper. And that's why this coefficient is negative. It's not that the newspaper have a negative effect on the response. What it means is that once we model the TV and the radio, the newspaper has this negative coefficient, but that doesn't mean that it has a negative coefficient or negative effect on its own. So again, this is why the multiple linear model is going to start being a little bit difficult to interpret, because you cannot just look at one coefficient and make statements about it, ignoring the others and ignoring what other factors you have in the model. You cannot just look at one, you have to look at the whole thing. And so in this case, in this model including three predictors, the RMSE goes down from 3.2 to 1.67, so it's about half as much, and that means we are reducing the error in the predictions of the model by about 50%, and the R-square improves from 61% to basically 90%. So that means we are now able to explain about 90% of the variance in the sales variable. So by all means, this looks like this is a better model, one in which we include the three predictors. And now when we face a multiple linear regression model, then we can also compute the residual sum of squares, the RMSE, and we compute the R-square. Everything is still meaningful with many predictors. But the thing is that, if you remember, we could start overfitting the model just by including more and more parameters, more and more features in this case. And this is something that we want to avoid. So somehow we need a coefficient or a measure of the model accuracy that takes into account the complexity of the model, the number of parameters that we have, so that in the process of building a model, we can look at that one and tell whether we are starting to overfit or not. And we have one called the adjusted R-square, the adjusted coefficient of determination, which is this R-square bar. And what it's doing is doing something very similar to before. So we got the R-square, but we are penalizing here in a sense by first accounting for the number of observations and the number of features, the number of predictors. So whenever P is large, this number is going to be lowered. And so in a sense, this adjusted R-square is going to correct for the spurious increase in the R-square just when we are adding more and more predictors. We know that that's something we want to avoid. So instead of computing R-square, you should be computing the adjusted R-square because it penalizes for P. And so that's essentially the essence of the linear model. How do we build a relationship in a linear fashion between an arbitrary number of features from 1 to P and the response Y? How we fit the model and how we can diagnose the model in the sense of looking at how good the model is with respect to predictions and explained variability. So now we're going to start talking about something a little bit more advanced, and that is what happens if the predictors, the X's, are not numbers. What happens if they are categorical variables? Because what we assume so far is that, again, we have the X's that are just numbers, and that's why we have the coefficients, the beta J's, interpreted as slopes. But what happens if they're not numbers? What happens if they're measured at a nominal level? Well, that, you know, they're also referred to as categorical variables or qualitative variables. How we incorporate these variables into the model is done by dummy variables. So there's this concept of a dummy variable that we're going to see in a minute. And by the way, if you come from a more computer science, machine learning background, this is what they refer to one-hot encoding. We're going to see why. And so whenever we have categorical variables, we are going to encode them with dummy variables. We're going to see exactly now. And whenever we have ordinal variables, so something that is in between a numerical variable and a categorical variable, what we typically do in a regression model is model them as both numbers and categorical variables. So whenever we have an ordinal variable, normally you include the number and the category in the model, so that the predictor acts both as a category and a number. And so what happens? What are the dummy variables? So imagine that we have some predictor X that is binary. It's, for example, something yes or no. It can only have these two categories, yes or no, success, failure, things like that. Then how we incorporate this into the model is by adding a new predictor. Let's call it X sub I. So for the ith observation, this new predictor is going to take the value of 1 if the observation is no, is of category no. And it's going to have a 0 if the observation is a yes. And of course, I'm assigning 1 to no and 0 to yes. This is completely arbitrary. It could be the other way around. It's just, what I chose here. But the point is, we get this categorical variable and we turn it into this one extra predictor. It's going to be equal to 1 if the category was no, and it's going to be 0 if the category was yes. So if you think about it, and this is the only predictor we have in the model, it will result in something like this. So the ith observation is going to predict it as follows. The intercept, one coefficient attached to this new predictor, it's going to be the same. There's going to be one beta 1 attached to that variable, and the error. And now if we look at the values for X, what we see is that this model is actually one of these two variants, either beta 0 plus the residual in the case of yes, because beta 1 would be 0. So this beta 1 that would be in there is removed because it's 0. If beta 1 equals 1, then that means we are, if X equals 1, then beta 1 is in the model because the X equals no. And so this is essentially saying, do we include this coefficient into the prediction or not? For one of the two categories, it's going to be there. For the other category, it's not going to be in there. And we control that by making this binary dummy variable. This is all it's going to do. It's going to make the model include beta 1 or not. So let's see an example. So here we have data about the salary of people as a function of whether they have health insurance or not. And what we see here with the box plot is that there appears to be this difference between the two groups. If you have an insurance, or people having an insurance tend to have a higher salary than people without insurance. And so we could build a model in which we model the response Y as a function of the insurance. Now it turns out that this X is categorical. So how we're going to do it is use a dummy variable. This dummy variable is going to encode specifically the case in which insurance equals no. So again, here the dummy variable would be 0 if yes, 1 if no. And so the model, if we fit the model, we have these estimates. We have beta 0 with a value of 120, and we have beta 1 with a value of minus 28. How do we interpret this? Again, when the dummy variable equals 0, the only thing that is active in the model is beta 0. And that will correspond to the case in which insurance equals yes. So this beta 0 is actually modeling the effect of X equals yes. And then beta 1 would be active in the model only for the case of insurance no. So it would be the effect of X equal no as a deviation from the baseline, from beta 0. So again, beta 0 would be measuring something like this. So 120 here. And beta 1 would be measuring this negative deviation of minus 28 units. This is what the model would do. Let's look at more than two categories. So imagine that the variable, the original X, is a categorical variable with more than two levels. So how we encode this variable into the model is by using more dummy variables, and specifically one per category of the variable. So imagine that we are measuring something like the marital status of the employees. They can be never married, married, widowed, divorced, etc. So what we do is include one dummy variable per category of the variable. So whenever the observation corresponds to someone who is married, x1 is going to be 1, otherwise it's going to be 0. Then we have this other variable, number 2, which is going to be 1, it's going to be active, it's going to be hot, only when the observation relates to someone who is widowed. And then we're going to have variable 3 equal to 1 only when the observation relates to someone being, I don't know, divorced. And so again, we have one dummy variable per category of the variable. And so this results in the following model. Again, we have the global intercept, and we have one coefficient per dummy variable, all the same. It has, again, the same shape of any other linear model. But it's important to note here that only one of these x's is going to be actually 1. Only one of them is going to be hot or active for any given observation. Because this is a categorical variable, it could be one of many categories. Only one of them is going to be active equal 1, because only one of them is going to have one of those values. So what you see is, again, what we have is a model in which we always have the intercept and then either beta 1 x1 or beta 2 x2 or beta 3 x3, only one of them. And so this is a way of modeling the effect of each of the categories into the response by using dummy variables. So let's see an example. Imagine that again we want to model the wage as a function of the marital status. This is a categorical variable and it has more than 2 levels, more than 2 categories. Specifically, we have 5. And so the linear model would be the common intercept again, and then one dummy variable for the case of married people with the corresponding coefficient, one dummy variable for widowed people with the corresponding coefficient, etc. If we fit the model doing ordinary least squares, then we have these coefficients. And again, the way to look at them is the first one corresponds to the value for people in the first group. So that's 92.7, would be somewhere around there. And then the others are going to be deviations from it. So this 26 means people in the group married, they have a wage estimated at 92.7 plus 26.12. So it's a deviation. Again, this beta 1 is a deviation from the baseline in the positive direction. Then we have widowed people, which have a positive deviation of 6.8. And that's this one here. And then divorced, and then separated, etc., etc. So again, this is how we can use a categorical predictor in a linear model. It's all the same, it's just we have to include these dummy variables. So there's one fewer dummy variable than the number of levels in the nominal predictor. So if you see this example here, the nominal predictor marital status has 5 different categories, but if you see, we only have 4 dummy variables. Why is that? Because the level with no variable, that missing level, is what we call the baseline. And all the others are modeled again as deviations from it. So the baseline here is the intercept beta 0. It's kind of saying that this beta 0 corresponds to the coefficient for the first group, for the never married in this case. And again, that's going to be the mean of the first group. So when using dummy variables to encode a categorical predictor, actually these coefficients are measuring the average of the response for each of the categories of the predictor. So this is the average for the never married. This plus this one is the average for married people. The baseline plus this one is the average for the widowed, and so on and so forth. They are measuring what is the average of the response for each category. And because we do it by using dummy variables, these coefficients are interpreted as deviations from the first group. Now, of course, sometimes we're going to be interested in modeling all levels exhaustively. So sometimes we're going to be interested in having the estimate of the average of the group without having any deviations or baselines or things like that. And this is something that we can do. It's just easier to interpret, and we do it by removing the intercept, by removing the beta 0. So now the dummy variables would not be deviations anymore, and we can do it. It's just a model like this, in which you see the first coefficient is going to be attached to the first group. It's not going to be a intercept in its own. It's going to be the coefficient for the first category. And you see it's going to be essentially the same thing, 92.7. That's what we were measuring earlier. The difference is in the rest of the table. The other coefficients are not deviations from the baseline anymore. They are the averages on their own. So just for comparison, you see here the the coefficient for the worst was 10.4 plus 92.7. So that's about 103, which is what we have here. So if we remove the intercept, it's important to understand that what we're doing is making these dummy variables, these coefficients, correspond to averages per group, not deviations from a common intercept. Again, sometimes this is easier to look at because we already have the numbers here. But what we will see is that as we increase the number of predictors, this doesn't make too much sense. And we have to model predictors in this way by making deviations from a baseline. We will see that later. So this is how we can incorporate categorical predictors in a linear regression model. You might have heard that a linear regression model is only between numerical variables. It's not. You can encode categorical variables in this way. It just turns into one dummy variable that can be only 0 or 1 with its corresponding coefficient for each of the categories of the categorical variable. And that's it. We have a linear model all the same. And the next thing will be interaction effects, but we are going to stop here and take a small break. So it's 11:30. Let's come back in 15 minutes, so 15 to 12, and then we continue with the rest of the lecture. Any questions that you have, again, the Q&A is open, so feel free to post them about anything, and I will try to answer them when we come back. So let's have 15 minutes, and then we continue with interaction effects. Okay, so we are back. So this far we talked about what the linear model is, how to fit the model, how to diagnose it, and we just talked about how to use categorical predictors in a linear model. What we are going to talk now is about how to model interaction effects. So let's see. First of all, maybe it's a good idea if I remind you what an interaction effect is. So when we have a model like this one, what we're modeling is main effects. So we have this beta 1 is modeling the main effect of x1, and beta 2 is modeling the main effect of x2. So this quantity, this coefficient, models the effect of the variable. Now what we saw is that there could be interaction effects between factors of whatever process we're looking at, whatever phenomena we are modeling here. And that means that the effect of x1 is not only this main effect beta 1, but it also depends on the value of x2. So the extent to which x1 has some effect on the response, it also depends on the specific value of x2. So it's like x1 and x2 have an effect that is mixed together, that you cannot just look at one without looking at the other. So what we have seen so far is only main effects. So the effect of a unit increase in x1 is always beta 1 regardless of the value of x2. So this is how much x1 is going to affect the response regardless of x2. Very often this is not true, and we have interaction effects. And again, what it means is that the total effect of x1 depends on the value of x2. And what we are going to do in a linear model is incorporate this interaction through another term, which is going to be their product, x1 times x2. And so the model is going to now turn into, again, the common intercept, the main effect of x1, the main effect of x2, and then the interaction effect. And it's going to be just one term like the others. It's going to be the product x1, x2, and it's going to have the coefficient beta 3. And if you think about it, you could just define a variable x3 equal x1 times x2, and just have that one equals x3. It will be just another term in the model, another variable. We just happen to know that it corresponds to the product of x1 and x2, but you could just look at it as sorry, as another coefficient beta 3 for variable x3. If we do a little bit of math here and we go to this other line, what we see is that now the effect of x1 is actually this much, and it's incorporating again the main effect beta 1, and it's incorporating also the intercept. The intercept, the interaction beta 3, that depends on the specific value for x2. So the total effect of x1 is going to be the main effect plus the interaction with x2. And vice versa for x2. If we do the math and now a group for x2 instead of x1, we're going to see something similar. And so here's how we can model the interaction between x1 and x2 using the product. Let me show you an example. Again, we're going to look at the data about sales and advertising. And if we model the interaction, we have the common intercept. So what are the sales when we don't advertise anything? What is the main effect of the TV, the main effect of the radio, and the interaction effect? If we fit the model, just doing least squares regression again, we have this table of coefficients. And we see that it's quite different because now the coefficient for the TV is quite smaller, if you remember the other one. And we have the radio as well, that is also smaller, and the interaction effect. By doing this, the R square, so how much variance in the sales variable is explained by the model, it goes from 0.9 that we had earlier to 0.97. So by including the interactions, we are gaining an extra 7% explainability in the model, or capability of explaining the variance in the response. And the RMSE goes from 1.7 to 0.9. So this is a model that, according to these statistics, the R-square and the RMSE, is better than the model with only the main effects. So how do we interpret? So in this case, the TV advertising has a positive effect on the sales, and it's kind of reinforced by advertising on the radio. So if we do the little bit of algebra that we did earlier, then the value for the TV has the following effect. We have the main effect, and then the interaction with the radio, whatever value we have for the radio variable, and vice versa for the radio. So this is the main effect of the radio, and again we have the interaction term. All those are multiplying the radio. So the total effect now is again the main effect plus the interaction. And so if you think about it, it's something like, you know, spending time or spending money advertising on the TV, it's going to have a certain positive effect here. And if we also advertise on the radio, it's going to reinforce that effect. So think about it. If you see an advertisement on the TV about something, you might be inclined to buying it. If you also see it on the radio or listen to it on the radio, you are more likely to listen to it. So it's kind of, it reinforces your likelihood of buying the product if you listen in both of them as opposed to only one. This is when the interaction effect is measured in this case. And what we have is that the hierarchy principle. And here what we see is that even if the main effects are small, let's say they're not significant, we're going to see in the next lecture exactly what we mean by this. If the main effects are very small, even so, if the interaction seems to be significant, you should always include the main effects in the model. So even if we have a model here in which this number is big and these two numbers are small, you should always try to include them in the model. So never have the model in which you don't have the main effects and you only have the interaction, because it's going to be very difficult to interpret this. And actually, there's a whole branch of people in statistics who say it doesn't even make sense to only look at the interaction. Just like there's other people who say if there is an interaction, there is no point in looking at the main effects. What we do typically is include all of them, because otherwise there will be some confounding between TV and radio in this case, and it's going to be hard to interpret. So whenever you see that the interaction is significant, it's important, always include the main effects as well. So this was the interaction between two quantitative variables, between two numerical variables. What happens if we want to model the interaction between categorical variables? Then we can do it, and it's all the same, just about dummy variables. So what we are going to do is include one dummy variable per combination of the two factors. So let's say here we have two binary factors, x1 and x2. They can be either yes or no. Then what we're going to do is, again, model the main effects and interactions. So we're going to have one dummy variable that is going to model the case in which x1 equals no. So this is just a regular dummy variable as we saw earlier for variable x1. Then we have dummy variable 2, which is going to model the main effect of x2. Just as we saw earlier, just two variables, their main effects, one for x1, one for x2. And then we're going to have a third variable, x3, that models the case in which both of them are a no. The specific combination x1 equals no, x2 equal no. This will be modeling the interaction. So again, this is the main effect of x1, main effect of x2, and this is the interaction. What does it look like? Again, it's going to be just a linear model. We're going to have the common intercept. We're going to have the coefficient for the first dummy variable, for the second, and for the third. And if you think about it, again, we had in this example two categorical variables which are binary. So the four possible cases that we may have for any observation are these four here. So what we say is that in the model, we're going to have this, the three dummy variables. And how do we use them? Well, whenever we have x1 equal no in here and in here, we saw that this dummy variable 1 is going to be equal to 1. It's going to be active. It's going to model precisely the case in which capital X1 equals no. We have the same thing for x2. Whenever x2 equals no, we saw that this second dummy variable is going to be 1. So in this case, this is 1. And then we had the interaction in which we said whenever both of them are no, then we have the active dummy variable for the interaction. So you see here we are again, by means of binary dummy variables, modeling the 4 cases that we can have with 2 categorical variables of 2 levels each. And in a specific case in which no dummy variable is active, so if this is 0, this is 0, and this is 0, still we're going to have the common intercept, which corresponds to this row here, to all yeses. This is what the dummy variable, what the intercept is modeling. It's again modeling one specific combination of the factors. And again, we could also fit the model without the intercept, but that would be adding yet another dummy variable, and it becomes harder and harder to interpret as we add more and more variables. But again, the case that I want you to see here is that if we want to model the interaction between categorical variables, we just add one dummy variable per combination of the 2. And so how does it look like? So imagine that we go back to this data set about the wage of employees. We were looking at the main effect of the health insurance earlier. We can also look at the effect of the type of employment. So is it in an industrial kind of work or is it an IT kind of work? So we have this other variable here. Let me call it x2, and this is x1. So we are faceting the relationship between wage and health insurance by the type of industry. So what is the model? If we want to include the interaction, we see again we have the common intercept, main effect of insurance, main effect of the type of or the class of job, information technology in this case, and then we have this third coefficient for the interaction, the specific case in which there's no insurance and the employment is about IT. So if we fit the model, we have the following estimates. So the first one is telling us what the intercept is. And this again corresponds, as we know, to this one specific case in which the dummy variables are inactive. In our case, this corresponds to insurance equals yes, and industrial job. So it corresponds to this one here. So beta 0 would be the average for this group here. This is beta 0. Let me actually clean a little bit. Here we have beta 0. And then what we have is the main effect of insurance. So whenever insurance equals no, then we're going to have a negative deviation from the baseline of minus 24 units. And that would be here, minus 24. This is beta 1. We also have the effect of working on IT. And what this says is that if a person works on IT, there is a positive deviation of 15 units from the baseline. So it would be the difference between this case and the baseline. So again, this was beta 1. Here we have a positive effect of 15. This is beta 2. And whenever we have the interaction, so the specific case of no insurance and working on IT, there is a negative effect of minus 4. And that would be this one here. Minus 4, this is beta 3. So you see, by including the interaction effect as a dummy variable, we can model here the average of each of the 4 groups in these 2 variables, the class of work and whether they have insurance or not. That's how we interpret the model again. It's all again about deviations. These are all deviations from the baseline, from the common intercept. What happens if we have the final case in which one of the predictors is a categorical variable and the other one is a numerical variable? So what we do here is essentially add an extra term. So it's going to be this one, in which we're going to have a different slope for the other level of the factor. So in this case, we have x1, which is numerical. So this beta1 is the slope for the numerical variable x1. And then we have x2, which is categorical. So this is the dummy variable modeling the other level of the factor. And then we have their product, beta3, with the coefficient beta3. So this is going to be the slope of x1 whenever the dummy variable is active. So this is going to be the slope of the other level in the categorical variable. Or even better, I'm going to say this is the deviation from beta1 for the slope of x1 when we have the other level of the categorical variable. And again, we could remove main effects and everything, but again, interpretations become next to impossible. So what happens when we have a interaction like this one? Let me show you. So imagine we have again the data set about the wage of employees, and this time we're going to model wage as a function of the age. So age is a numerical variable. If we fit the model, then what we have is an intercept of 81. So that means for x equals 0, which is around here, the line crosses at around 81. And then we have a positive slope of 0.7. So for a unit increase in age, the wage increases by 0.7 units. There's a positive correlation, so to speak. So if we have this model, what we have is one intercept and one slope. That's it. What if we want to start including extra variables in the model? So let's say that we go for modeling the categorical variable insurance. We know how we can do it. We can just have the common intercept, which would correspond to the salary when age equals 0 for insurance equal yes. So what we have here is, let me draw again, for the age of 0. In red, we have insurance equal yes. So it will go over there. This is beta 0. So what is the intercept for the first group, for insurance equal yes? Then we have this deviation for the case insurance equal no, and we see that it's a negative one. It's a minus 26. So that means this blue line, if we draw it until x equals 0, it would be minus 26 from beta 0. So what we have here is just two different intercepts, one for each of the levels of the categorical variable. And we have one common slope. The age slope, beta 1, is 0.56. So this is measuring the slope of the two lines. And if you see here, comparing to the black line that we had earlier in this simple model, what we have is essentially now two lines that are parallel. They are parallel because we have only one coefficient for the slope. And we have two intercepts, one for each group. So we have the baseline here corresponds to yes, and then a deviation from the baseline corresponds to no. So in this case, two intercepts, one common slope. What we have again is two parallel lines. So we're modeling separately the relationship between age and wage for the cases in which there is insurance or there is not. And we are assuming in the model, we are forcing the model to make the same relationship with age for the two of them. It's just one is going to be higher than the other, but they're going to be parallel. There's no interaction here. What happens if we include the interaction? So maybe the relationship between age and wage is different between people with or without insurance. This would be an interaction. And this would translate here into the lines having two different slopes. Then we can model it all the same. It's just including an extra term here, beta 3, for the interaction. So again, we would have beta 0 still corresponds to the intercept for the yes insurance group. So it would be the intercept of this red line. Then we have the deviation from the intercept for the group without insurance, and we see that it's minus 38. So it would be extending this line minus 38 from the baseline. Then we have this slope for the first group for age equal yes, and that's a 0.45, it would be the slope of this red line. And then here we have the deviation for the group of no. So it's a 0.3 deviation from this 0.45 for the effect of the H in group no. So that means this slope here is 0.45 plus 0.3, so 0.75. So again, this is how we can model the interaction between these two factors, the H and the insurance. In the case we have one of them being categorical, it corresponds to these kind of models in which we have one intercept, two slopes, only one slope, one intercept, etc., etc. And we can force these, sorry, we can force these kind of relationships in the model by including intercepts or not, by including these interactions or not. And of course, we could have this model in which we have one common intercept and two slopes, because let's say that it makes sense that for both groups, whenever the x variable equals 0, then both of them must have the same value in the response. Let's say that because of whatever domain knowledge, we know this has to be the case. You can enforce this in the model by saying both of them are going to cross in the same point. This is going to be beta 0. And then we're going to have one slope for the first group, for the red line, and a deviation for the second line, which is group no. Again, this is something that if it makes sense, given the domain knowledge you have about the problem, you can enforce it into the model. You could say, let's have only one slope, one intercept and two slopes. This is possible. But again, what I want you to see here is that the linear model, it might look like something very simple, but you can extend it very easily by including dummy variables and interaction effects, and you can start having more complicated things like this. And we're only talking about two features here, two predictors, the H and the insurance. Of course, you can start throwing in a lot more variables in here, more categorical variables. We could have the marital status, which had 5 different categories. We can have many other variables, and the linear model remains the same. It's just a matter of properly interpreting the coefficients. And in any case, the whole thing could lead to a table that is huge. It's going to be very difficult to interpret, but we will see in the coming lecture how to make it easy to interpret the effects of all these variables whenever you have many more factors involved and interactions and everything. So for these kind of situations in which we may have multiple groups, multiple slopes, multiple intercepts, etc., there's something called hierarchical models that are also known as multi-level models or mixed effects models. And they are models specifically designed to cover these cases. And you can think, for example, about the typical case textbook example in which we want to study the test scores of students, but there is some kind of structure in the observations because we can put students that are together in the same class. We could have that group of students, and we know that also different classes are in different schools and different regions of the country, things like that. So whenever we have this kind of structure in the data, that the observations are not independent of each other, because two students, if you look at them, they are in the same group, maybe they are in the same school, but different groups, things like that. And so we might be interested in modeling what is the effect of the group, what is the effect of the school, what is the effect of the region. And in those cases, there are more powerful tools, hierarchical models, that we are not going to cover here in this course. But anyway, just FYI, this would be the more proper way to analyze that kind of data. So whenever there is this inherent structure in the data, you might be looking for hierarchical models for more powerful tools. And in general, one needs to be very careful when interpreting interaction effects, especially of more than 2 factors, because tables like this are going to start growing a lot, and it's going to be very difficult to interpret precisely what each of these coefficients is giving you, because one might be tempted, for instance, to say that this is the average slope of the H, but it's not. It's of one specific group. And whenever you start having more factors, x3, x4, etc., this is going to correspond to one specific combination of all those factors. So it's going to be more and more difficult. Again, in the next lecture, we're going to talk about this. And in general, we have to be very careful with interpretations because we know we can't just simply look at the coefficients because of what we saw earlier. Remember, everything else being equal, you can only look at the coefficient when considering all other coefficients of the model. You have to think about the coefficients holistically within the whole model. And we have to be careful with comparisons because the coefficients depend on the scale of the variables. Just think about it. If we have one variable that is measured in meters, the coefficient is going to be different from the same variable measured in kilometers. It's going to be a 1,000 different, a 1,000-fold difference. So you have to be very careful when looking at coefficients. Remember, they also depend on the units of measurement. So something that might look like 10 times bigger than something else is just a matter of the units. And it's going to be very, very difficult to look at the coefficients in imbalanced or unbalanced data sets. And this is why, again, the study design is important, to make sure that you have a properly designed study such that you don't have imbalanced data, because the coefficients are going to depend on this. You might be in a situation in which you think you are measuring some difference between A and B, but actually it's not. And again, the example I gave some lectures ago, imagine that we have a factor A and a factor B. And in A, we have only two levels, A1, A2. In B, we have two levels, B1, B2. The proper way of doing this would be a balanced data set in which we have the same number of observations in all four quadrants. But imagine that we have something like this. So there is a lot more observations here than in there. If we see any difference between A1 and A2, so we have one dummy variable in this case, remember, for A2, for A1. If we see a difference in there, most likely what we're seeing is a difference between B1 and B2, or the other way around, because in this case, A1, we have an overrepresentation of B1, and in A2, we have an overrepresentation of B2. So whatever difference we see between these two, it's confounded to some degree with the difference between B1 and B2. So it's going to be very tricky to make these comparisons. We have to be very careful with it. We're going to talk again about it in the next lecture. So typically what we're interested in is in whether there are differences across the levels of a factor, like in here, between A1 and A2, or how big they are. And again, this is going to be tricky with imbalanced data. In the next lecture, we're going to see how to do this kind of comparison properly. And finally, we can talk about transformations. Why? Because despite of what many people say or think, a linear model that has something like x squared is still a linear model. So we may add nonlinear effects just by transforming our variables. So we could do something like x to the power of 2, x to the power of 3, the log of x, 1 over x. We can do things like that. It's going to be useful if the relationship between the response and the predictor is clearly nonlinear, like we saw in the case of the TV advertisement. The relationship clearly was nonlinear, so we might try to transform one or two variables. The important thing here is that the model is still linear if the relationship among the variables is linear. So the word linear refers to the relationship between each of the terms in the model. It doesn't refer to the relationship between x1 and y. It refers to the relationship of the terms in the model. So if you have a model like this, in which you model the log of I as a function of x1 and the square of x2, this is still a linear model because the terms, these three terms, are related linearly. They are just, additive. And you have one coefficient per term of the model. So this is perfectly fine. This is still a linear model. And the good thing is that it's going to give us a much higher flexibility. And if you're still not convinced about it, just think about, imagine we have a table, table of data. We have one, the response, x1 and x2. If you include this x2 square in the model, it would be just the same as having this other variable, x3, that equals x2 squared. Now, Maybe you don't know that this is actually x2 squared. Maybe you don't even know this one. You have knowledge about it, but that knowledge about it is useless when you're fitting the model. You could very well call this beta 2 x3, and it would be fine. It's just another name for this vector of numbers. This is still a linear model, regardless of how you transform each of the variables. Now, what is not a linear model is if you have something like, I don't know, x minus 3 divided 1 minus x2. This is not a linear model because the term here contains two variables. Or something like x to the power of beta 1 x2. This is not a linear model because the terms are not linearly related. We have a question. What about the interaction? Is it still a linear model when those are included? Yeah, it's a linear model because they are linearly related. So it would be the case in which we have beta 0 plus beta 1 x1, beta 2 x2, beta 3 x1 times x2. It's still the same. You have one term with its coefficient, plus another term with its coefficient, plus another term with its coefficient, plus another term. It's all the same. And again, you could have very well pre-compute x3 equals x1 times x2 and just use x3 here. Sorry, x3. It's all the same, it's just a different name. This has other consequences for the model in terms of collinearity, we call it, but still the model is linear. It's linear because the relationship between the 4 terms in the model, or actually I should say 5 terms because this is another one, is linear. It's a linear combination. Each term with its own coefficient, and that's it. So you can start transforming your variables, no problem. So we consider x1 times x2 another variable. Yes, exactly. Would a model that has something like b1 x1, b2 x1 squared, b3 x2 be linear? Yeah, that's linear. So let me just show you, for those of you who don't read the Q&A, we have this model, beta 1 x1 plus beta 2 x1 squared plus beta 3 x2, I guess. This is still linear because we have one term with its coefficient plus another term with its coefficient plus another term with its coefficient. This is a linear model. Again, the problem here is that we have collinearity between those two. And that means essentially that these two terms are going to be correlated. And that could imply other problems for the model. But the model is still linear. So why is this useful? It's useful, for example, in the case of the relationship between sales and TV. So here in black, we have the linear model, just, sales equals beta 0 plus beta 1 TV. Just a line. And we saw that it had problems, especially around here. One can think about transforming both the response and the predictor. So what happens if we have this model? We are transforming the response and we are transforming the predictor. So the model is now going to be the red line over here. It's going to be nonlinear in this case. We're having a nonlinear relationship, but the model is still linear because we have one term with its coefficient, another term with its coefficient, another term. So this is still a linear model. It's just we are transforming the variables before fitting the model. Because again, if you look at this, you could just compute y prime equal the log of y. You could compute x prime equal the log of x, and then fit the model with y hat and x hat. It's the same thing. You're just transforming the variable before fitting the model. And it will be fine. It will be something like this red line over here. What happens, if you want to visualize it better, is that if we transform the two variables, like in this case, we're actually plotting a linear model in the transformed space. So if we transform the TV Here you see that we are plotting TV on a log scale, and we are plotting sales also in a log scale. So this would be what we talked about, sales prime and TV prime. It's like transforming the data and then fitting the linear model. This red line here corresponds to that one. So this non-linear or this curve here in the linear scale is actually a line in a log scale. This is what we're doing. We are transforming the variables before fitting the model. So if you look at the transformed variables here, we're just fitting a line. It's all the same. What happens, of course, is that the very observations are transformed. So it's a different model. And this could be useful, for example, in the case of modeling the wage as a function of the age that we saw earlier. We had this straight line, and we see that clearly that's not a very good model because we have this kind of concave pattern. But of course, we could have this other model. So we have age and age squared. And again, this is a linear model. We have one coefficient, or one term with its coefficient, one term with its coefficient, one term with its coefficient. The relationship is linear, it's all the same. And so the one in red would be the model that we're fitting with this quadratic term on it. We see that it looks like it's a better model. And actually, if you look at patterns in the residuals, R-squares, and that kind of thing, you're going to see that this model is better than the other one. And it's fine. Fitting the model, diagnosing the model, it's all the same. So when should you transform? That's a good question. So the point is you have to diagnose a model always with a scatter plot of residuals versus fitted value, the one that I told you in the beginning. And if you see patterns in the plot, that suggests transformations or the need for other variables. So imagine here we have this toy example between variables x and y. We have some observations, and then we could choose a straight line, just a linear model, no transformation. That would be the red line over here. That would be fine in principle. Now, the problem comes when you plot the residual by fitted value. And you see that there's a very clear pattern in the residuals. Again, this plot should be kind of random, a random cloud of points. If it's not, that means there's something you could do about it. And sure enough, what this is telling us is that here for small values of x and small values of y, the model is underestimating. And somewhere in the middle, the model is overestimating. This is why we have this pattern in the residuals. So what this is suggesting is you could try a quadratic transformation in the model, or a log transformation. Again, if you look at the lecture on supported data analysis, you had in there kind of guidelines of which kind of transformation to apply in each case. So for this case, we have a quadratic model, I believe it was, and in blue, we now look at the residuals, and indeed, it looks now much better. It looks like the random cloud of points that it should look like. So in principle, again, you could fit a simple model. If you look in the residuals that there is something going on, try transformation, and you may end up with something like this. And as we mentioned, if you see a random cloud of points like this, but like a cluster of points around there, another cluster of points around here, things like that, that's typically suggesting that you're missing another variable, a third variable, one that is probably categorical, and it's just the difference between these observations, and these observations. That kind of pattern you're going to see when you look at the residuals. So again, in the case of the TV, if we fit just this regular linear model, just a straight line, what we have in the residuals is something like this. And we see that there's something going on. Of course, this is not random. When we plot the log-log model that we saw earlier, the pattern in the residuals looks like this. So now we see that it's random around the horizontal axis, so it's kind of random in there. This is a much better model. Still, we see the problem that for increasing values, it's increasing variance. This is something else. This is what we call heteroscedasticity, or non-constant variance. That means that the variance in the residuals is a function of the fitted value. Again, we're going to talk about it in the next lecture, but this is a separate issue. What we see here is that the randomness of the residuals around 0. That's what we want to look at here. Yeah, so there's something wrong. Again, we're going to talk about it in the next lecture. So to sum up what we saw today, we saw the linear model. And this is going to be, again, the basis for a lot of the statistics that we do in the course and in real life. We saw what happens when you only have one feature, one predictor, and how to interpret it. What happens when you go to multiple predictors and how it becomes increasingly difficult to interpret, and how to fit the model, how to do variable selection, things about dummy variables to encode categorical predictors, interaction effects, and transformations. How you can still fit a linear model, no problem, if you transform your variables properly, and how that could lead to better models, as we see in cases like this one here. And of course, as always, we have some further reading to do if you want. You could read chapter 3.3.3 called Potential Problems of the book. This one is going to tell you about some of the things that I was mentioning today. So transformations, collinearity, the case in which there is correlation between predictors, heteroscedasticity, the problem that we saw in which the variance in the residuals is increasing with well, increasing or decreasing. In general, there is a pattern with respect to the variance. Things like that. So how to deal with those problems in regression. And if you want to keep reading about regression models, I can suggest these two books. This one here is a kind of older book. They're by the same people, as you see. But the good thing about it is that it talks in length about multi-level and hierarchical models. If it's something that you might be interested in reading about, this is a very good model. If you want to, limit yourself to only regression in general without going to the hierarchical case, this is a book that they published just this year, and it's kind of the regression part of this book expanded into its own book. So look it up online. You might be able to find something more interesting. And this is about the lecture today, about the linear model. In the next lecture, we're going to use this as a foundation to start looking into more statistics. What happens when we start talking about distributions in the response, distributions in the coefficients, etc., etc. So if you want to look at it that way, today we looked at the linear model from a mathematical perspective, just what the coefficients are and what they mean. And in the next lecture, we're going to talk it from a statistical perspective, talk about distributions and standard errors and that kind of thing. So this was the lecture today. As always, I'm going to remain here for a couple of minutes. If there is any question, just feel free to ask in the Q&A, and I will try to answer them. And if not, see you on Wednesday.